All right, so this is Physics 1B for September 14th. We're going to start off by talking about this problem that we had before the break. All right, so we have a 200 centimeter cube glass flask that's filled to the brim with mercury at 20 degrees Celsius. How much mercury overflows when the temperature of the system is raised to 120 degrees Celsius? So we go from an initial temperature of 20 degrees Celsius to a new temperature, call it the final temperature, just T, of 100 degrees Celsius. And we're given that the coefficient of linear expansion for the glass is that. All right. And we're supposed to figure out how much mercury overflows. And in this problem, we're going to think about both objects expanding, just like we did in the last problem. And the relationship we'll need for this is that the change in volume is equal to beta times the initial volume times delta t, where that beta is equal to 3 times alpha, and alpha is what's given here. And then we probably also need to know what the alpha value is for mercury too, right? Or beta for mercury. Let's see which is given here. So mercury is, this is the value for beta, 18 times 10 to the negative 5. So we'll put that in here. All right, you guys want to take a few minutes to try to solve this? Okay, someone got an answer. Say it's 2 centimeters cubed. Anybody else get the same answer? I'll just ask John, did you include both the expansion of the mercury and the expansion of the glass? They're both going to expand, right? Okay. Okay, someone got a different answer. That's good. You guys are all getting different answers. Okay, well, Tyler and Ange got the same answer. 2.7 centimeters cubed. How did you guys do it? The two of you got the same answer, Tyler. How did Tyler or Ange, one of the two of you, how did you do it? What was your general strategy here? All right, so you found how much the glass and the mercury would expand, and then subtracted their volumes to find how much mercury would overflow. That sounds right. Kenny's saying he got a math error. That's understandable. But you did the same thing. Okay, so you're in agreement that that's what we need to do. Okay, so we need to figure out how much each expands and then find the difference, and that should do it, right? All right, so we're going to have the change in volume for which one's going to expand more. Is it going to be the glass or is it going to be the mercury? Why does it do that? That's so annoying. All I was doing was typing and then it just... I wonder if... Okay, I need to slow down. If I just do... Did I move it somehow? I don't know. I really don't know what happened there. Apologize. Okay, so or something like that. I was typing the beta. I'm assuming it's because my palm is touching this thing and maybe it, I don't know. So beta for the glass is going to be 3 times this, so it's going to be 1.2 times 10 to the negative 5 degrees Celsius inverse. So the, I didn't mean to do that. The glass is definitely not going to expand as much as the mercury. Okay, so delta V for the mercury minus the change in volume for the glass. That's basically going to be what we're trying to solve for. So delta V mercury, we just plug in beta for mercury times the initial volume, which will be the same for both of them, times delta T, which is also the same for both of them, so I'll just call it delta T, minus beta for glass times V naught delta T. We pull those out, so you basically you're just doing beta of the mercury minus beta for the glass, multiply by the initial volume times delta T. Does this look right to you guys, or did I make a mistake? It's really easy for me to make mistakes when I'm doing this stuff. I'm often not using my brain. It's in Kelvin, but it's the same value in Kelvin and in Celsius, by the way. If we go back to the table, the main thing is that 1 degree Kelvin and 1 degree Celsius, like the temperature, don't mean the same thing. But the change, like the change in Celsius and the change in Kelvin for 1 degree is the same, right? And that's kind of emphasized. Oh my god, so something happened where... What happened here? So whatever happened down here at the bottom that changed the size of... those windows change the size of these windows too. OneNote's really weird. I'm sure it's a user error thing. I'm sure I'm doing something wrong. Okay, sorry to distract. Kelvin or Celsius, basically. You see that here? It does not matter, basically. So you don't need to convert it. You do not need to convert it because the deltas, the change in temperature, is the same on both scales. Does that make sense? Man, I'm having a hard time explaining stuff today. All right, so I think I'm just going to distract by all these other things. So beta for mercury was 18, minus beta for glass was 1.2. They both are multiplied by 10 to the 5, so we'll pull that on the outside. 10 to the negative 5, sorry. The initial volume was 200 centimeters cubed. So we put in here 200 centimeters cubed. And then delta T is from 100, so it's basically, I'll put 100 minus 20, but we could just immediately put 80 if you want. Okay, so that I'm assuming this gives you 2.7, as they're saying. That's the amount of mercury and they make the point in this problem to say that this is part of the reason why a mercury thermometer would work, is that the amount that the mercury expands is quite a bit more than the amount the glass expands. And so as a result, the mercury can be a pretty accurate measurement of temperature, basically, right? Although we don't really use mercury thermometers anymore, like I was saying earlier, due to the fact that mercury is a health risk. I think the mercury vapor, if you inhale it, it's really dangerous, right? Is it like, what can it do? It can cause cancer. It's been a long time since I read about this. What do you guys know about mercury? Do you know anything about mercury? It's something people used to play with a lot back in the 50s and stuff, but nowadays they know it's quite deadly. Anyway, so good problem. Just shows that you find the difference here, and that's pretty much it. Have you guys never played with mercury before? See, Baron has an answer. The liquid form of mercury is especially dangerous because it vaporizes. Yeah, so it's the vapor. If the vapor is inhaled, it's easily absorbed, and when it first gets into the lungs and they're in the blood, into the brain, the nerve poison can cause sleep disorders, agitation, and paralysis. Paralysis sounds bad. So it's poisonous to our nervous system. As long as you don't inhale it, I guess you just, now that we all have masks, as long as you put on your mask, you're good. People get mercury poison from eating fish. I think fish can get into there, yeah. I don't know. When I say play with that, I mean like when I was a kid, we had a mercury thermometer in my house. It was just a standard thermometer that was used for, checking if we had a cold when I was a kid or whatever, or checking temperature. And it broke and it fell on the floor, and all these little mercury droplets like spread throughout the room. And so I got down on the floor and I took my thumbnail and I just like pushed them all together. It's fun. It's a really weird fluid, right? Because it has anyway, if you take little droplets of it and you push them together, they just merge into bigger droplets. It's basically like in Terminator 2. Is that movie so old? Do you guys watch that movie? Anyway, one of the like Terminators in Terminator 2 is made of liquid metal, so there's a scene when he heats up, and that's basically what mercury does. Yeah, it's a boomer movie for sure. Because the boomers, they're like my parents, but somehow it's a boomer movie based on modern meaning of what that means, I guess. No, you weren't really kidding, but that's okay. I understand the joke, and I'm willing to go along with it. I'm not going to try to... Yeah, the modern definition of boomer, which means you're in your 30s and 40s, right? All right, so... a moomer? What's a moomer? I'll just say I'd rather be a boomer than a zoomer. Millennial boomer. Okay. All right, so there's the volume due to temperature change kind of a problem. All right, so what's next? I think we're getting into calorimetry now, right? Yeah, we did thermal expansion, so now we're going to talk about calorimetry. Specific heat, molar specific heat, and all this stuff. That's what we'll do for the next 30 minutes or so. All right, so there's a lot of stuff for this. I'm just going to make sure real quick that I think, we did everything. We did all the problems that I had here. So I pulled a bunch of stuff from your textbook for this because I don't feel like writing a bunch of stuff out, and this has literally everything we need to know about what we're going to talk about next. So we're just going to take all this stuff, we're going to kind of read through it together like we did last time in class. Oops, there we go. Okay, the first thing I wrote down here, and I'll expand this so it's a little bigger. Make it bigger so it's one line. Okay, so we'll start off by saying, by defining what the word heat means. Heat is something that is, it kind of means different things, whether you're talking about, I don't know, if you're going to talk to your friend about heat versus what we mean in physics. If you like listen to the news, or if you listen to people use the word heat, they might say things like, I see heat waves rising off the street, or they'll say, I don't know, what's another example? How is the word heat used maybe in the wrong way outside of physics? Okay, there you go. That's a completely different thing versus what I was just saying. That's good. Heat rises. Yeah, that's a good example of, and what's wrong with that statement? When they say heat rises, what would be the more appropriate way of saying that? What do they mean when they say heat rises? Mm-hmm. What if you're using it to describe hot air? Yeah, hot air does rise. That's true. That's right. Yeah, but heat itself doesn't rise. Yeah, exactly. So people will use the word heat like a noun. I think it's not a noun, right? Is it a noun? It's a noun, but they'll try to use it as if it's something that's tangible, like if it's something you could touch or something like that. They'd be like, I can feel the heat. Maybe that's not that bad of a way of saying it, but in physics, when we say heat isn't a thing, Rouge is saying, right? Yeah, it's not a thing. It is a process, really, right? I think heat itself can be a noun, but saying heat isn't a thing is a good way of putting it. So the way we define heat in physics is an energy transfer that takes place solely because of a temperature difference. So when you have two objects that have different temperatures, there's going to be heat that flows. Heat is a noun because it's energy. Yeah, it actually is a noun. I'm sorry. Me saying that it's not a noun is the wrong way of saying it. Saying it isn't a thing is a better way of saying it. So suppose you have a hot object and a cold object, right? And you put them in thermal contact with each other, okay? So you've got, it could be boiling water and you drop an ice cube into it or something like that, right? So let's say I have an object that's 100 degrees Celsius, like water, and I put an ice cube up next to it, and let's say the ice cube is 0 degrees Celsius. Because there's a temperature difference, there's going to be a flow of heat that goes from the hot to the cold. So the heat's going to flow in this direction. Okay, and I probably even said it wrong there too. It's just that there's going to be a transfer of energy from this object to this object, and the amount of energy that's transferred is going to be some amount of heat that we're going to call, I think commonly in this class, we're going to use the symbol Q for this, I believe. Anyway, but it's like a heat flow, an energy flow from hot to cold until the two objects come into some type of, some type of equilibrium. All right. Now, one thing that was realized historically, so I guess technically this picture comes before the words right here. The question would be, how do we quantify the amount of heat that actually flows from the hot object to the cold object? And something that was figured out by a guy named Joule was that if you take a vessel of water and you stir it really vigorously, then you can increase the temperature of it. All right? And a lab that, I don't know, I did this lab when I was at Oklahoma State. We did a lab where we would set up a system something like this, where we would have a string wrapped over a pulley. Okay, this is something you're probably familiar with, pulleys and masses, right? And then this pulley would connect to a something that could turn right here. And then what we would do is you'd drop a heavy object from some height, like maybe a meter or two. And then after dropping that, you would measure the change in energy of this by measuring the temperature, by measuring the new temperature of this. Have you guys done this before? You believe some blenders heat up liquids? Are there blenders that actually warm things up? I mean, a blender by itself would naturally warm things up. I don't know if there's blenders that literally like heat up coffee and stuff like that, or something like that. Cider. Blenders can cook eggs. I can believe that. Like just a normal blender, you just drop some eggs in a blender and leave it on long enough, it'll cook the eggs. Is that what you're saying, or is it like special? Oh, interesting. Has anyone done this experiment before that I'm describing right here? Did anyone, like, did you do this in high school at all? Or did you do it in your chemistry class? We don't have this in the physics department, but it'd be a really cool lab to do. It's really impressive because quite literally what you can do then is you can say, you can quantify exactly how much the temperature of the water increased based on the change in potential energy of the mass. So the mass drops by some distance, right? It decreases its potential energy. But that potential energy goes into kinetic energy that rolls this. That kinetic energy causes this thing to spin, and then the temperature of the water goes up. And so you can have a direct connection between energy and temperature. That's what's important here, is that there is a relationship between energy and temperature. They're connected to each other. And Joule figured that out. And he realized, well, if I can measure energy and I can measure temperature, then I can come up with a way to connect them, right? There must be some way that I can connect them. All right, and so here's the definition. It's like a long definition, which is why I pulled this out of here. And then, of course, the connection would be, obviously, you can increase the temperature by heating it up, too. So that's the connection between energy here, more specifically work done, and heat. And Joule realized this connection, that temperature increases were connected to energy. All right, let's read what this says right here. It says, we can define a unit of quantity of heat. Quantity of heat would be the amount of heat, right? Based on the temperature changes of some specific material. So you pick a material, in this case, water. The calorie, which is something you guys have heard of before because we use it to describe the energy contents of food, is the amount of heat that's required to raise the temperature of 1 gram of water specifically from 14.5 degrees Celsius to 15.5 degrees Celsius. All right, that's what a calorie is. The heat required to raise the temperature of 1 gram of water from 14.5 to 15.5 degrees Celsius. A food calorie is actually a kilocalorie. So what we will down here call a calorie is actually 1,000 calories. When you see on food, when it says that something has 1 calorie, actually often the way that the kilocalorie is described is with a capital C, calorie. Like on the back of food, I think usually it looks like it says caloric, but I'm trying to say calorie with a capital C. It's a kilocalorie. Okay. And then they also bring this other thing up. I don't know if this will ever matter to you guys, but I don't know. Maybe you'll work in a field where you need to know about this, but there's a corresponding unit of heat that uses Fahrenheit and British units. It's called the British Thermal Unit, or a BTU. 1 BTU is the quantity of heat required to raise the temperature of 1 pound of water from 1 degree Fahrenheit from 63 to 64 degrees Fahrenheit. Hey, BTU, I saw that on the AC. Yeah, I suspect that, when you go to buy things, they actually might measure how strong it is in terms of BTUs. Yeah. Because heat is energy in transit, there must be a definite relationship between these units and the familiar mechanical energy units, such as the joule, and so there is. 1 calorie is 4.186 joules. 1 kilocalorie is 4,186 joules. So if you think about, like, if you eat like 1,000 calories in a meal, you're eating, so like 1,000 calories from a meal, keep in mind that's actually 1,000 kilocalories. That would correspond to, and this would be what, like, I don't know, a burrito at Chipotle maybe, or something like that. This would correspond to 4.186 times 10 to the 6 joules, right? So 4.1 million joules. That's how much. It kind of gives you an idea that the joule is a very small amount of energy relative to the amount of energy that we actually ingest on a daily basis, because what's a normal? What does it say on the side of boxes? It says something like based on a 2,000 calorie a day diet or something like that, or I don't know what it says these days. 2,500 calorie a day diet. So you're actually eating in the millions of orders of joules, tens of millions of joules of food a day. Okay. And then it also has the relationship for the BTU. I mean, this is written here. I don't know that any of the problems in this textbook use this. I don't know. I haven't done the problems from this chapter in this textbook before, but just keep in mind that BTU is just another kind of thing that's like calories, and in a way, it's really just another measurement of energy. Do you guys have any questions? Your Gatorade says it's 150 calories with a capital C, right? So that's 150 kilocalories, or whatever 150 times this number is. Okay, so to just kind of tie this all together, there's a relationship between energy and temperature. We use the phrase heat to describe what happens when there's an energy transfer that occurs solely based on temperature difference. And we use these type of units down here. You don't have to use the calorie, technically. All right? But 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by this amount, okay? So it's a type of energy. You can always get away with doing everything in joules, though. But you may be given things that are in calories from time to time. All right? You heard about turning heat into electricity, like body heat, but it's really weak. Yeah, there's some processes by which you can turn heat into electricity. There's a lot of them. So the simplest version of how you can turn heat into electricity is by a generator. Should we talk about what a generator is? So a generator is something that basically you have some cold object and you heat it up, and the effect of heating it up produces some kind of mechanical change, and you can use that to generate electricity. And the idea is basically like, suppose that I take a vessel and I put into this vessel some water, and suppose that it's kind of like a kettle in the sense that there's some kind of spout right here, right? And then we heat it up by burning something. What you burn, it can be really anything, but usually in the United States and other countries, what we're burning is fossil fuels. So you burn some coal. So we got a bunch of coal down here. You burn the coal, or you burn natural gas, or whatever you're going to burn, and it has the effect of heating the water up, so you get water vapor. Water vapor contained in this closed container will eventually start to spew out, just like it does whenever you heat up things in a kettle. So you get steam coming out of here. And of course, that steam has got a lot of energy associated with it. So what you can do with the steam is you can basically connect it to a turbine. So what's a turbine? You can think wind turbine if you want to. It's basically the same idea. But instead of being turned by wind, it's going to be turned by steam. So this thing right here is going to turn like this. So you're going to get motion, right? And now that you've got motion, you've got a type of energy, right? You've converted the heat into mechanical energy. And when this thing turns, the next thing that you need is a magnet and some coils. So then this is connected to a magnet. So you connect this to a magnet. So you've got spinning, right? So once you've got spinning, you can take your magnet, which is going to have a north end of a pole and a south end of a pole. Maybe even the way this is designed, maybe you could make this like the north end pole of the magnet. This is the south end pole of the magnet, so it's connected. And then all you really need after that is a big coil of wire. So then you encase this whole thing in a big coil of wires. It's a good color for wires. Or even you could even just have a bunch of coils of wire right here, really. It worked just fine. But you got a bunch of coils of wire, and then the net effect of this is that it's going to light things up. So you could, for example, have a light bulb right here. That's a generator, basically. So you take some substance like heat. You heat up water. The water causes or the heat causes the water to change state into a gas. The gas turns a turbine. The turbine has like magnets on it, for example. You put those magnets next to a coil, and the effect of that is you get electricity flowing through the circuit in the form of electrical current. So that's one way you can turn heat into electricity, Tom. I don't know if that's what you're thinking of, but there's other ways as well. You can also pull heat out of this process here, just the direct transfer of hot to cold. At its core, an engine works off this process. Yeah, we call this whole thing here a generator. And almost all commercial power in the United States is generated in just this way. Except for solar power, which is a little bit different. Okay, so we talked about how... Did that answer your question, Tom, at all? Were you thinking about something else? You were saying, like, body heat. Like, body heat can produce electricity? Yeah, I suppose there's probably some tiny amounts of electricity you can produce. You can definitely produce electricity as long as you have a system in which you have a temperature difference, basically. But yeah, it might be kind of weak if you're just using body heat. Okay, so what's next? Next, we want to talk about calorimetry. And for that, I pulled these two guys here. So we'll talk about this, and then we're going to do this problem here. Maybe a couple problems. I think we'll have time maybe for two. So the next thing to talk about is specific heat. So I said we're going to use the symbol Q to represent heat, and specific heat is defined by this equation here, which says that Q, the heat required to change temperature of a certain mass, is equal to the amount of mass multiplied by C, which is the specific heat. I'll define what that means in a second, and then multiplied by the temperature change. And you see in this little box right here what everything represents. The value of the specific heat has different values for different materials. I'm pretty sure I grabbed somewhere here. Yep. Boy, that's a big table. Wait, does that even have specific heats in it?